So before we officially start class, well, registration for the September classes has started officially from today. So if you would like to reserve your spot in September, just have your parents WhatsApp us and I will send them this flyer and the registration form. And you all could go through it and sign up if you wish. All right, but anyway, let's move on. Today's main work, which is half life. Okay. All right. And of course, if you have any questions about registration, we'll handle it after class. I just want to get straight into the theory this morning, right? And morning to, well, everyone. All right. So let's talk about half-life. And usually when I start this topic, I start with the graph, right? So I want everyone, you don't have to draw the graph or anything like that. But let me try to explain why this graph is slowly sloping downwards. Let's say we take a sample of radioactive material. All right. So let's take a block of it. We go to the radioactivity store, if there's one, right? And we ask them for a block of something that's radioactive. Now, if it's radioactive, it means that all the atoms inside the structure is radioactive or unstable. And of course, when an atom is unstable, it will shoot out radiation, whether it be alpha, beta, or gamma, right? So you have alpha, beta, or gamma, right? The type isn't too important right now. And of course, as it shoots out the radiation, the atoms will slowly move from being radioactive to not being radioactive. So I have a question. Over time, right? Let's say when we now buy the block, everything is radioactive within the block. And we wait about 4 days. So we come back 4 days later. Will the block be more radioactive or will it be less radioactive? What do you all think on the chat? You come back 4 days later. Will that block be more radioactive or less radioactive? Right, and half the class is saying less, and well, I'm reading through, and some people are saying more. The answer is actually less, because over time it's given away radiation, right? So think of it as a bright bulb. It's like a bulb that's giving off light, and over time it's losing its light. Let's just say the bulb is getting old. So over time it's going from bright and becoming dimmer and dimmer and dimmer, right? So over time, because the block is losing radioactivity, because it's giving it away, over time, it will get what? Less radioactive. For those who got it wrong, you understand now? If you are radioactive and you give off radiation, think of radiation as money. You start off with a lot of money, so you are very radioactive, but you start giving away your money. Over time, you become less and less and less rich. Okay? All right. So, and this is what the graph is showing. Look at the graph. The graph is slowly sloping downwards. The y-axis is basically at the end of the day telling you how radioactive it is. You can forget about the label and whatnot. The point is to keep it simple. The y-axis is telling you how radioactive the block is. And the x-axis shows what happens over a span of time. And over time, it gets less and less and less radioactive. Hence, it's sloping down. But that's not the end of the story. There's actually a nice pattern, right? And let's look at the pattern. And it has to do something with the word half in it. So when we now buy the block, let's call the amount of radioactivity 100, right? So 100 just means full radioactivity. And every few minutes, we begin to measure the amount of radioactivity left. Now, here's the thing. How much is half of 100? 50. Let's see how long it took to move from 100 to 50. Let's see how long. Let's go. I'm gonna get a different color here. How long did it take to reach 50? Anybody can read it off the graph? I think it's 4 minutes, right? So check this out. To go from 100 to 50, it took 4 minutes. I think everyone can see that, right? You can clearly see it in landing on 4. Now, we are over here at 50%. Let's ask ourselves now, if we are at 50, how much is half of 50? Well, half of 50 is 25, right? So I'll put 25 here. How long did it take to go from, listen to the question, a lot of people get this one wrong. The question is, how long did it take to go from 50 to 25? The answer is not 8. Remember, we are standing at 50. At 50, it was 4 minutes. How long did it take from this point to reach 25, which is half of 50? And you will see it's roughly how much? It lands on 8. But from 4 minutes to 8 minutes is another 4 minutes. Okay? Now we are standing at 25. How much is half of 25? Well, half of 25 is about 12.5. And roughly how long did it take to do that? Right? It's an approximation, right? My graph not perfect. It takes us to 12 minutes. But remember, we were at 8 minutes. And how long did it take us to reach 12 minutes? That's another 4 minutes. You'll notice the 4 minutes is consistent. It seems that whatever value we are at, to reach half of that value always takes the same amount of time. And that time, 4 minutes, is known as your half-life, right? Now, here's the thing. There are many different radioactive substances out there. Let's call a few, well, there's one like carbon-14 that have, another one, uranium, different types of uraniums and whatnot that are radioactive. Some substances have a short half-life, like some substances have a half-life of 2 minutes. So every 2 minutes, you can expect the amount of radioactivity to decrease by a half. For example, if you started off with 70% radioactivity and you come back 2 minutes later, you will have 35% radioactivity because half of 70 is 35. And it will keep halving every 2 minutes. Now, it has some substances that have a very large half-life. For example, and we're going to bounce this up today, something called carbon-14. Carbon-14 has a half-life of roughly 5,370 years. Try to imagine that figure. That means every 5,370 years, the amount of carbon-14 that's radioactive will be reduced by a half. All right, which is a very long time. It way exceeds a human lifespan unless you take care of yourself, you eat properly and whatnot, right? Okay, so if they ask you what is a half-life, let me just read it through to make sure you understand the definition, right? The definition is everything I just said. Half-life is the interval of time required for half of the atomic nuclei of radioactivity. This just basically means half the amount of radioactivity to decay by a half, right? So I want everyone to take down the definition, right? Half-life is the interval of time required for half of the atomic nuclei of a radioactive sample to decay. And in case you can't remember what decay means, decay basically means it's shooting out radiation. That's all it means. Decay means you have something and it's either shooting out alpha, beta, or gamma. You get 2 marks for writing back this definition in the CXC exam. Let me know when you are finished. Okay. Now, here's the thing, right? Radioactivity is a random process. And it gives the illusion that at a certain amount of time, it is consistent with the amount of radioactivity decreasing by a half, but it has some randomness in it. Let me explain what we mean by random. Random means certain things about half-life cannot be predicted. Let's assume, right? Let's assume that we take a radioactive sample. So we went and find a rock, and the rock was radioactive. Now, to keep it simple, a radioactive rock or any rock in the world will not have 4 atoms. It's going to have billions and billions and billions of atoms. Obviously, I don't have time to draw all of them. So let's just say we take a rock and we keep out, let's just assume it has 4 atoms in it. So clearly this is a very, very small rock, but we're keeping our eyes on those 8 atoms. For this explanation, everything that is red is radioactive, right? R for red, R for what? Radioactive. When something gives off radiation, it's no longer going to be radioactive, which is blue. So we consider blue a dead atom, meaning that it's not radioactive. Let's assume that the half-life is 20 seconds. So we're going to assume that the half-life over here is 20 seconds. I'm going to put here half-life. Sorry for the little squeeze there. What does a half-life of 20 seconds mean, right? It means that every 20 seconds, half of the radioactive substance available will give off radiation and change into something else. So let's start here. We start with, I'll put 1 here. We start with 8 radioactive atoms. 20 seconds have passed. Look, I have the time, the scale here. The x-axis is time. I even label it time. We started off with 8. Half of 8 is 4. But here's the thing. If you were standing over here, do you think you could predict which half will change? Look at it. Look at this here. It seems that 1, 2, 3, 4 gave off radioactivity and became, well, dead. I'm calling it dead. And if we wait another 20 seconds, look at this. Remember, at this point, we have 4 radioactive atoms, the red ones. After another 20 seconds, half of that 4, which is 2, is supposed to give off radioactivity and become dead. So out of these 4, 1, 2, 3, 4, it seems that these 2 gave off radioactivity, and now you're left with these 2. Another 20 seconds need to pass, and half of the remaining radioactive atoms, which is 2, right? Well, half of 2 is 1, is going to give off radioactivity. The thing about it, you cannot predict which one of them will give off radioactivity. But it seems that he did, and he is the lone survivor at the moment. If we repeat this experiment, we are going to get different results. Keep your eyes over here. So we take another 8 radioactive what? Atoms. We give it 20 seconds. So when we check back 20 seconds later, pretend you close your eyes and you just open it 20 seconds later. So you have no idea what went on between here and here. You just open your eyes at 20. You all notice it's a different half that gave off radioactivity compared to the one above. In the one above, it was 1, 2, 3, 4. But now it's these 4, 1, 2, 3, 4. And then we close our eyes for what? 20 seconds again and reopen it at 40, 20 seconds later. Out of these 4, these 2 gave up their radioactivity, well, radiation. You all notice it's a different pattern. And then obviously at another 20 seconds, there was a different winner than the one above. The point is, every 20 seconds, every half-life, half of the remaining atoms did give up their radioactivity. It's just that we cannot predict which half. No scientist at the moment can actually predict which half will give off radiation. All we know is within a certain time frame for that substance, half will give off radiation. It's just, once again, we don't know which half. Everyone okay so far? So that's random. Random means you cannot predict it. You cannot predict which half will give off the radiation, right? But before we move to the next slide, right? Remember when you all were trying to imagine that half of the atoms were changing into or giving off radiation. I told you to imagine that between here and here, you will close your eyes. And of course, when you open your eyes, you're going to see half of it disappear or change into something else. So that's the closed eyes concept, meaning that you have no idea what went on between here and here. How about we investigate this small time frame now? The first 20 seconds. The first 20 seconds. Because it's kind of misleading. And hear what I mean by misleading. A lot of people think that between here and here, just before the 20th second, nothing happening, nothing happening, nothing happening, and then bam, 4 change. Do you all think realistically that that is what happens? Or do you think that they change one by one slowly between the 20 seconds? I think that it will be more like that, right? You have like between here and here, it have 4 of them that need to give off radioactivity because half of 8 is 4. So one by one, between the 20 seconds, they will give off radioactivity. But let me show you why that is still confusing. So look at this diagram. You probably think that nothing changed, but look at it properly. Notice that my time is going from 0 seconds to 20 seconds. So that's the closed eye period. So let's pretend we take a peek, right? When it's changing. All we know is that within the first 20 seconds, 4 has to change. And look at it. At 0 seconds, we have all 8. At the 4th second, 1 of them change. At the 12th seconds, our next one change, making it total 2. Then at the 16th second, a 3rd one, and finally, on the 20th second, the 4th one change. So within the half-life, 4 of them gave off radioactivity. Let's try that same experiment again. At 0 seconds, we start off with 8. At the second, 1 of them gave off radioactivity. then at 6, then at 8, and then at 14. Now, I know the half-life is 20, but at the 14th second, it achieved its goal, meaning that half of it changed to something else. So that means for the remainder of the time, nothing else will change. But when you open your eyes here, and when you open your eyes here, all you are going to see is that half of them will change. So how is this random? Simple. It's random, meaning that we don't know at what time the atoms are going to give off the radioactivity. It's bad enough we don't know which half will give off radioactivity, and now we don't know at what time. All we know is within a specific frame of time, half of it will change to something else. Everyone okay with that? Right? That this one is totally different from the first example. The first one was random in terms of you don't know which half is going to change. And the second example, this one, deals with the timing of which ones will change. So draw this one properly. I'll give you another 5 minutes. All right, so let's see the summary to all of this. And this is what I was trying to say with all those fancy diagrams. Radioactive decay is random. In other words, they use instead of random in some textbooks, right? It's spontaneous. They basically mean the same thing, right? And look at it. One, it's random in 2 ways. One, the exact time of decay cannot be predicted. So you don't know at what time, in my example, within the 20 seconds. Also, like we said, you cannot predict which half is going to decay. If you do the experiment 1,000,000 times, every time you do it, you're going to get a different result. Now, with us, we only did it with 8 atoms. Obviously, in real life, like I said, it's billions and billions of atoms, not 8, okay? And the thing about it, the radioactive decay, the random nature, right, is not affected by temperature, pressure, or chemical conditions. Even if you raise the temperature, you will realize the half-life, it will remain the same. The pressure remains. If you increase the pressure, it just doesn't affect the experiment. I've seen this question only come twice in the CXE exam, so I know it's a valid question, right? So take down everything on the screen, and of course, let me know when you are finished. Something a little more interesting, a little more colorful here. Anybody here ever dreamed of being an archaeologist? Digging up bones, dinosaur bones, or fossils, looking up for old pottery and whatnot. Anybody ever had that dream? One person said yes, and one person said no. Sorry, paleontology, hear me. Archaeology. Well, that's the actual name. Thanks, Nikin. You know my how my vocabulary is. All right, so let's go through some basics here. Let's say you want to become an I'm just going to use the word archaeologist, right? Even though probably the correct thing is paleontology, right? All right, so let's talk a little bit here. Here we have a caveman, right? And he's nice and happy. Everything is going great in his life. But one day he has to die. But let's talk about when he was living. When he is living, obviously he's exposed to the atmosphere and his surroundings. So you ever hear the expression, you are what you eat? Meaning that whatever you consume or take in basically becomes a part of you. And this is what happens to all living organisms, right? Whether it be animals, whether it be plants. In our environment, there's two substances you can definitely find. Carbon 12, that's C12, the C stands for carbon, and there is C14, carbon 14. How it works is that carbon 12 is not radioactive. So carbon 12 is not radioactive. I spell radioactive wrong, right? It's not radioactive. But its brother, carbon 14, is radioactive. Okay? Now here's the thing. If something is not radioactive, like carbon 12, right? Do you think it will decrease over time? You think about it, while the caveman is living, he's breathing in, he's eating. So what happens? The carbon 12 and the carbon 14 gets stuck within his bones. It gets fused into his bones. But because carbon 12 is not radioactive, the question is, over time, will the amount of carbon 12 decrease, even if he's dead? What do you all think? Right? It will not increase and it will not what? Decrease, because it's not radioactive. So here's the thing. When we discover, look, we have a little skeleton here, right? When we discover his remains, what scientists will do, they will take a sample of his bones and they will analyze it. And they will try to see how much carbon 12 it has in it and how much carbon 14. So let's say you are this scientist or archaeologist or whatever, and you drill into his skull and you analyze it. Upon analyzing his skull, you realize this is the amount of atoms of carbon 12 it has. I use some simple numbers to make the explanation easier. So let's say in that small sample you took, there were 2,000 carbon 12 atoms. When the caveman was living, how much carbon 12 do you think he would have in his body? When he was dead, we found 2,000. So when he was living, how much do you think he had? I just ask you. Let's use a little bit of science skills here. It will be 2,000 because carbon 12 is not reactive. So the amount of carbon 12 throughout time, even though he is dead, will remain the same, right? So that means we can predict that when he was living, he also had 2,000 atoms of carbon 12 in his skull, right? Now, scientists have worked out a ratio, right? They found that in all living things, there's a ratio of carbon 12 to carbon 14, right? The ratio is a really, really complex number, like a really scary number. But let's just assume it's 5-to-1. The 5 is for the carbon 12, the 1 is for the carbon 14, which means that in any living organism, for our made-up example, the amount of carbon 14, the radioactive one, will always be 5 times less because it's 5-to-1, right? So we're going to assume the ratio is 5-to-1. So, but this is only for when the organism is living. Can you all predict how much carbon 14 the caveman will have when he was living? If the amount of carbon 12 is 2,000, we can more than use the ratio to predict how much carbon 14 he had when he was living. Right, it will be 1/5, right? 5 times less. We just have to take 2,000 and divide it by 5. So in case you're unsure, take 2,000 and divide it by 5, and you will get 400. Now, what we really care about now is the carbon 14. So when this caveman was living, right, the amount of carbon 14 was 400. But when we discovered him, Years later, how much atoms did he have? 53, which makes sense because carbon-14 is radioactive, meaning that over time, it got less and less and less, and finally it reached to what? 53. So my question to you is, how do we calculate how old these bones are? And it's very, very simple, more simple than you think. All we need to know is this. The half-life of carbon-14 is roughly 5,730 years. I think I had mentioned that previously. So look at this. Keep your eyes on the carbon-14. When the caveman was living, he had 400 radioactive atoms of carbon-14. After the first half-life, and how much is a half-life? 5,730 years. He just died. So 5,730 years later, half of it disappeared. So half of 400 is 200. But that's only after the first 5,730 years. Now, another half-life passes, another 5,730 years, and this 200 needs to be halved. How much is half of 200? 100. Then finally, another half-life passes. So 5,730 years. And half of 100 is 50. But 50 is so close to 53. I mean, for all reasonable purposes, we could stop there, right? Because 50 is so close to 53. How much years pass? You just have to add up 1, 2, 3. And that will tell you how much years have passed. So how much years did pass? Right? And of course, this is for the carbon-14 we're talking about. The carbon-12 not going to change. The only reason we care about the carbon-12 is so that we could predict how much carbon-14 it had when it was living. Right? So 5730 added 3 times, and we get this amount. So these bones are this old. It's 17,190 years old. So that caveman died a long time ago. Now, before you start to take down everything on the screen, right? Now, obviously, you don't have to draw the stone hedge in the background, right? You just draw the caveman, everything else, basically, right? You call this procedure carbon dating. I'm sure you have heard it at some point in time. But carbon dating, you could only use it to date the age of living things, meaning that you can only use it for what? Things like a caveman, a human being, an animal, a plant. You cannot use it to date how old a stone was. That's a totally different technique, right? Because a stone was never living. Whatever for carbon dating to work, it had to be living so that it would take in carbon-12 and take in carbon-14 by breathing and eating, and it got fused within the living organism. Question, could you use it to tell the age of a wooden table? What do you all think? Some of you are going to fall for this, but the answer is yes. You could use it to what? Tell the age of a wooden table. Now, I know you're probably saying, well, a table doesn't live, but it's a wooden table. Didn't the wood come from a tree? A tree at one point in time was living. So yes, you can use it to tell the age of a wooden table, right? Right? What the scientists will do, they will take a sample out of it and they will analyze it in the lab, right? Difference. You see how in this example, we were looking at the number of atoms itself. Like it started off with 400 atoms, and then it was what, 200 and then 100. But at the end of the day, right, we could do the same question or same type of questions, but instead of looking at the exact amount of atoms, we can express it as what? A fraction. And sometimes, well, actually a lot of times in the CXC exam, they express it as a fraction. Let me show you what's going on here. Let's say that we're walking one day in the forest and we found some old fish bones here, right? That was the best picture I could get. And, right, we're trying to estimate the age of the fish bones. So let's just skip to the part where we figured out how much carbon-14 it had when it was living. But the examiner is going to say this. We know when it was living, it had a certain amount of C14, carbon-14 in its bones, right? And over time, the amount of carbon-14 got less and less and less. But at the point of finding the fish bones, that's supposed to be 1/16. It had 1/16 of the carbon left. Now, we don't know the amount of carbon-14 it had, like the examiner didn't state it. All we know is it has 1/16 of whatever it had. Do you think we can calculate the age of these fish bones? And it's very, very easy. When the fish bones was living, the amount of carbon-14, we're going to represent it with 1. The number 1 means it had all the carbon-14. After the first half-life of 5,730 years, how much would be left? Only half, because half of 1 is a half. After another 5,730 years, half of the half will be left. How much is half of a half? If you have half a cake and somebody steals half, how much will you be left with? A quarter. Do you all think you all could continue this pattern for me until you reach 1/16 and then calculate how old these fish bones are? Right? And once again, I just want to point out, it's different from the first example because we don't know the actual amount of atoms. Instead, we're discussing the question as a fraction of the atoms that's left. So see if we can do this question and send the answer, the final answer for the age of the bones for me. So after another half-life, 5,730 years, half of a quarter is 1/8. And then finally, after another 5,730 years, half of 1/8, which is 1/16. We have reached the required value. So how much years we passed? Let us add up this 4 times. So the answer would have been 22920 years. Right? For those who got it wrong, I think a few people went another one by mistake. They went one more 5,730 years. But at least let me know that you saw your mistake, and then we will move on. Right? So everyone take down the working, and I think after this we have a lot of calculations to do. All right, so let me explain what's going on in this question here. Right? Before you get scared and whatnot, it looks really complex. This here is basically an equation for nuclear energy. And the aim of this question is to try to figure out how much energy is created in this nuclear reaction, right? Whether it be a nuclear bomb or nuclear factory or whatnot, right? Everything here boils down to a formula, the Einstein's famous formula. How much people have seen this? E is equal to m multiplied by c squared, where the E stands for energy, m for the missing mass, well, change in mass, right? Now, the missing mass has to be in kilograms, and c is the speed of light. And in case you didn't know, but the speed of light squared, and this squared only belongs to the letter C. And the speed of light, you have to remember, well, I think you should try to memorize this value. 3 multiplied by 10 to the power 8 meters per second. As you all know, light moves very, very quickly. All this formula basically says is that if any mass goes missing, the missing mass is converted into energy, and this formula allows you to calculate that amount of energy. But we have to be careful. The mass has to be measured in kilograms, right? Forget the table for the time. I know it's kind of hard to see the values. I had to put in some decimal points here, right? Let me write it a little bit bigger. This value is 235.118. But the mass of uranium is given in U. U is something called an atomic mass. An atomic mass is not in kilograms. We will need to convert it to kilograms. This value here is 89.947. This one here is 143.881. And this here is 1.009. And what you're seeing below here is 1.66 multiplied by 10 to the power minus 27 kilograms. So what usually happens in a nuclear reactor is that you start off with uranium, a special type of uranium. And well, the uranium we're using today is uranium-235. And what you will do, you will take the uranium and shoot like a bullet towards the uranium. Now, think of it like this. You shoot a bullet at something, and whatever it hits, it's going to split into different pieces. The uranium is going to split into krypton, I assume this is barium, and you see it have a 2 here? It splits into 2 neutrons. That's what the 2 means here. And you get some energy with it. Right? So I'm hoping I have a little diagram here. Right, so this is what happens. This here is the uranium. You are going to shoot a neutron at it. So the green thing is the neutron. When the neutron hits the uranium, get a little, pretend you see a little explosion, and you see 2 things come out here. One of them is going to be krypton, one of them is going to be barium, and you get how much neutrons? 1, 2. But here's the thing. Some mass goes missing, meaning that one side, these 2 things are going to weigh a certain amount. They're going to have a certain mass. But when we add up everything on the other side, we get less mass, which means, like I just said, some mass goes missing. Let's try to figure out how much mass goes missing. But we are going to calculate it in terms of U, an atomic mass. This only looks scary, but let's take it one side at a time. What's the mass of 1 neutron? The examiner was so nice to give it to us. 1.009. And what is the mass of the uranium? 235.118. Do you all think you could take your time and add up these 2 values for me and tell me how much is the total mass? But the mass will not be in kilograms. It's going to be in terms of U, which is okay for the time being. Add it up and send your answer on the chat. Right, this is what I am getting, right? Of course, I think I'm getting what the majority of people are getting. I'm getting 236.127 U. Now, after the reaction or explosion or whatever, we get krypton, we get barium, right? So what's the mass of krypton? The mass of krypton is how much? 89.947. The mass of barium is 143.881, plus we have 2 neutrons, and each neutron is 1.009. Add up all 4 things here and tell me what's the mass afterwards. Right. So just to recap, all we are doing is adding up the masses before, and we are adding up all the masses after. And the masses will be given to you by the examiner. So someone said I did something wrong. 0.94. Oh, yes, you are correct. This is supposed to be a 7. Right? So mass, total mass before, which we just calculated, and now we're trying to get the total mass after. So let me pause it and add it up. All right. So before the reaction, we had these, the total mass was 236.127. That is this guy. And afterwards, even though we had 4 items after, this was the mass. Do you all notice the value got a little bit smaller? Look at this one. You can see from the first 3 values. It was 236, and afterwards we had 235. So that means it seems like everything got lighter, which means some mass went missing. Do you all think you all could calculate the missing mass in terms of of atomic mass? What do you think you have to do with the 2 values? You just not add. Who said add? If you're trying to figure out how much is missing, like if I have 8 apples and then after it had 6 apples, how do you figure out how much apples it have? You simply minus. So when we minus the 2 values, we could figure out how much is missing. So you have 236.127 minus 235.846. I am getting this amount of missing mass, 0.281 U. That is how much mass went missing. Now, what Einstein is saying, what did say, sorry, is that whenever mass goes missing, it is converted into energy. And we can use this formula now to calculate the amount of energy. And I'll show you how to type it in on a calculator as well. To calculate the amount of energy created, we take the missing mass, but we have to make sure and convert it to kilograms. So here's what. You have to take the 0.281, but we have to convert it to kilograms, which means we have to multiply it by 1.66 multiplied by 10 to the power minus 27. That is this value. This is how you convert U's to kilograms. And we have to multiply it now by the speed of light squared. Now I'm running out of space here. Right? Let's see if I can. And the speed of light, make sure I put it in brackets. It's 3 multiplied by 10 to the power 8. Close your brackets and do not forget to press the squared sign. Right? I know it's a lot to take in, right? But this is just one of the many examples that's going to be coming up. And even if you're lost, right? Remember, you can always review the recordings, right? And slow it down. And anything you missed, I guarantee I would have said it. All right? It's just a kind of rushing it down as how it's our last class. And I really, really want to get this example out of the way and have it recorded at least. So let's try to type this in on our calculator. I have my calculator here. Right? There's a lot of writing here. Now, when you're typing in this, right, you see this multiply by 10 to the power minus 27. Whenever you want to type in multiply by 10 to the power something, you have to press the EXP button on the Sharp calculators. The Casio calculators will have a multiply by 10 to the power button. But just watch how I do it on the sharp calculator here. I have 0.281, so I'm typing in that 0.281 multiply by, what am I multiplying it by? 1.66, right? I should probably put this in brackets so my calculator doesn't mistake it with anything. Open brackets, 1.66. Now I'm not going to press multiply by 10 to the power minus 27. I'm going to press EXP. When I press the EXP button, right, you all notice a multiply by 10 comes up automatically. Now I just have to type in the minus 27, but it's not this minus sign, it's this minus sign, the plus or minus button. Minus 27, and I close my brackets. So I'm up to here now. Then I'm going to press multiply, open brackets, 3, multiply by 10 to the power 8. But that's my EXP button. I press 8, close the brackets, and then I do what? Squared. I have a squared button over here. Then I press equal. Please confirm you're seeing this on your calculator. Make sure you see it. The final answer for this question is this amount of energy. 4.19814 multiplied by 10 to the power minus 11, and energy is measured in something called joules, right? Joules, right? Someone asks why this value. It's a standard value. It's like, let me give an analogy. If somebody were to ask you, how much centimeters in a meter? Your answer would be 100 centimeters. And now if they ask you, why 100? Well, you're going to get stumped because you just grew up knowing that 100 centimeters make a meter. But the question is, why 100? That's similar to this question, right? 1 U is just equal to this amount of kilograms. It's a value that came up with over time. So anytime you're seeing 1 U, to convert it to kilograms, you just have to multiply it by 1.66 multiplied by 10 to the power minus 27. Now, don't get me wrong. There is a good reason why that value is equal to 1 U, right? Just like how there is a good reason 100 centimeters is equal to 1 meter. Why those are the reasons, I'm not qualified enough to explain that. I really am not, okay? But you could always research it, and it's a more historical development of why certain values are equal to a certain amount of other values. And that's supposed to have this one here. I put 2 1s by mistake. Yes. All right.